like, yeah, you only need to do 4 things. Like 4, you could literally just take 4 classes. And then the next year, it's like my year. It's like, no, you have to do 8 things, 4 of which can be classes.
You're being recorded, by the way. So whatever you say is online, shared with the web. I signed up for the virtual chemical society meeting, you know. And this guy's, so the mic's live and he's like talking, he doesn't realize that one of the speakers, the thing didn't work, like he can, like, so it was like a whole 40 minutes blank, you know. But the guy's there talking, he's negotiating some kind of deal with the guy, you know. It's pretty weird. Like, anyway, so you got to be careful, I guess, these days.
Nothing I say is a real hot take.
You never know. I mean, you never know who's listening, you know. So, didn't that happen to some like prime minister or something? Something happened.
Oh, I'm sure.
I forget who it was.
Whenever you throw Zoom in there, it's just like court proceeding or, you know, government meeting. I've seen a lot of those stories.
Yeah. Oh yeah, the Supreme Court, it happened, right? Someone, I forget what happened.
Like, kids takes a dump or whatever, and like so on.
Yeah.
And everybody hears the toilet flushing. In this, I think that's what it was in the Supreme Court. Like they went to that.
Yeah, that's it. Yeah. It was, they were
but like
at home,
in the actual courtroom, you're not allowed to leave.
Right.
So they have like a recess.
Anyway, so let me get started. So anyway, I gotta wear a mask. Like, I don't know, I'm paranoid. But anyway, that's how it is. I'm diseased too, so it's kind of like helpful just to wear a mask. But anyway, so anyway, oh, the homework. So anyone have problems with that thing, or do I need to go through that again? There's a problem with it. Someone brought up. Where's the homework now? Down here somewhere. So he's got this, you're asked to get these power things, and this one, the A2 is this molecular weight, blah, 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 and this is negative here, 10. So it's 3 by df to the minus 2. So that's a wrong, it shouldn't be negative, because if you go back to this book thing, can I get rid of this? Let's see, I want to go to 135 or something, right? It just says 128. Pretty sure it was 135. I don't know why I can remember numbers in this thing. So that's intrinsic. Then he does A2, 134. And then he gives this equation, right? So it's m to the minus 2 and rg cubed, and rg goes with m to the 1 over df. So it's 3 by df minus 2 is A2.
So I think if you go to page, I think 154.
Why is it we can remember the numbers in this thing? It's weird, isn't it? Like, I don't usually remember, but somehow.
Because he defines another variable that is like it's A2. It's another A2. I think it's nothing before. I just saw it. Stop right there.
That's the same equation, though, right?
Yeah. So if you see, if that minus A sub A2, I think they like confuse because of that.
Oh.
So they said to the exponent of negative A, which negative A is just the fractal power. So I think they like mix up their sign.
Yeah. That you're right. That's where he mixed up the sign. Yeah, that's a good point. Anyway, it should be that. Anyway, his sign's wrong, right? We agree on that. Okay, so Sorry, you can put something like that in your answer, like
Question. When you ask about the relationships, though, we're using, like in the homework, we're using 19, 20, and 21, right? There isn't a question about that equation.
I think there is. Oh, all right. Yeah, 19, 20, and 21 are the values for that equation.
Right.
So yeah, maybe, oh, so you already did it and you didn't need to know that. Yeah, you're right. So those are just the values for that equation. Just minus 0.55, because you have to calculate DF, I think. So if you calculate DF, it'll come out wrong. Unless you switch the sign of that other thing. Anyway, that's kind of the only thing. I don't know what else. I don't remember what else is on this, but there's no other question. That was a question that came up. I thought I'd kind of, I don't know, should be just kind of work through it.
I actually do have one more question.
Okay.
It was, oh gosh, what was it? I think it was part B. You were talking about how to get, equation 18. And in the notes or in the video, so that first equation, that eta equals eta naught, 1 plus intrinsic viscosity times phi. So in the video, you wrote it as 1 minus intrinsic viscosity phi.
Oh, should be
just a mistake.
Yeah, it was a mistake.
Okay, I
yeah.
wanted to make sure, because I was trying to find that, thinking
no,
maybe there was a different relationship that was separate from that one.
No.
Okay.
So yeah, so I can go through that equation right now because that's kind of what I'm doing for the other thing. Is that it for the quiz though, or? So anyway, so you have, if you have just the idea, like you have a box and you're flowing something through it, right? And then if you put something in, and say you put concrete in, and it just fills up the bottom like that much. Right, so that fraction of it would fill up, and then you get like less volume here. Right? So that's displacement. So what happens to the viscosity? So if you didn't know about that, so this is a black box then. Right? So you didn't know about that happened. You'd say like the viscosities, so actually you just have the flow rate is proportional to the viscosity. Right? In other words, the flow rate is proportional to 1 over the viscosity. So your flow rate would drop by that fraction. In other words, the higher the viscosity, that's Poiseuille's law, the flow rate goes with 1 over the viscosity. Which is why it's also this flow rate is like mass per time, right? So you can say that like time and viscosity are proportional to each other. Right? So anyway, this is simple in my mind, but when I try to talk about it, it seems to be pretty complicated. So you just say you're going to displace, so this flow rate would drop by that fraction. It would be like that divided by that fraction. Right? So I just call that F. So I want to use the volume fraction. So so anyway, that means that if you ignored that, that would mean that your viscosity would just be kind of reduced by that fraction, or increased by that fraction. So you get that less flow rate, I mean the higher viscosity, and the fraction would kind of decide it. So if you say you have like 100% plus whatever amount that you displace, so your amount is going to depend on the amount that you put in, so like mass per volume. And that's some factor that decides, because you're not dealing with it. If it's a solid object like concrete, then it's just the volume fraction, right? Mass per volume. But your polymer or some other fractal thing is going to have like a bigger volume is bigger than what the volume of what you put in. So it's not just the mass times or divided by the density to get the volume. It's got this difference because it takes up this extra space. It's got entrainment. Doesn't it have entrainment? Right, the time change and like a week off And like somehow my brain is kind of cooked. Anyway, so this is an entrainment, right? So that's called the Zim model. Zim's a guy, Bruno Zim, from the 1940s. He came to the US to escape the Nazis, went to Brooklyn Polytech, kind of founded Polymers in the US. Got a next door neighbor named Bruno too. There's only 2 Brunos I know. This is it must be a German. I'm not sure what nationality Bruno is, but anyway, so it's kind of the Zen models. It's totally in training. So you could take like the coil size, like end-to-end distance, right, and then cube it, and that would give you that volume then, because it totally entrains everything within that thing. Right? That's one option. The second option is it's only the chain that matters, like the structure of the chain that matters. There's nothing entrained. So there's no entrainment. There's no entrainment, right? So these are going to, this will give a higher displacement volume than that one. So this is sometimes called the Rouse model. And then in that case, the volume is kind of proportional to the molecular weight. In this case, the volume is going to be R end distance cubed, and that's going to be the molecular weight. Since its size is molecular weight to the 1 by fractal dimension, so it's going to be to the 3/2 of Gaussian chain, or 2-dimensional. So you get 2 different displacement volumes per mass. You get this kind of conversion factor for mass per volume. It'll be volume per mass. If you follow the Zim model, the volume is going to be R cubed, and the mass is mass. So end up with this molecular weight to the A, where A equals 3 by df minus let's see, this is it's going to be 1. A is going to have units for -1, and then the volume is going to be 3/2, so 3 by df. That's 1. -1 is because you divide by mass, because it's mass 1 over mass concentration, mass per volume. So then the 3 by df is a cube of the end-to-end distance when you're using the Zim model, non-draining model. All right. So anyway, if you put that in terms of the viscosity, you have the measured viscosity, then you divide by that fraction to get the actual viscosity. So that fraction is 1 plus the volume fraction times this number, which is this volume per mass of the object, this thing. So it's just a displacement, like your thing displaces. So it's like you put in concrete here. So if this is solid, right, the df is 3, 3 by 3 is 1, 1 minus 1 is 0, so it's just a number. Any number to the 0 is 1, right? So you just have some constant. It turns out that number for spheres, if this thing was filled with spheres, say, so the displacement of the spheres is going to be 2.5 times the concentration, because it's voids in spheres, the closest packed spheres. And so, and then if it's going to be a polymer, then this thing will have different values. Like that A will have different values. So you have theta state, right? It's going to be 0.5. And if you have a good solvent, so then this is 5/3. So that's 9/5 minus 4/5 is 9/5 minus 5/5 is 4/5, and times 2 is 8/10, so 0.8. You could solve it. Let's say it's a rod. Then it's df is, for a rod, let's see, for a rod, this thing's going to be 1, so it's 3 minus 2. 3 minus 1 is 2. So rod, so you go from, this thing has a pretty weird behavior. Like you go from a rod, it's 2, and it's a power, right? So it's got a big impact. then you kind of crinkle up the rod, and all of a sudden it goes to 0.8, big drop, and then then you go from that to the coil, and it's 0.5, and then if you get to the collapsed coil, then it's just 0. It doesn't depend on the size of it anymore. It doesn't have enough weight dependence. Supposedly the free volume is the same for all spheres at 2.5. It's the way it weights the concentration. So this should be really simple. Like it seems to be pretty complicated the more I look at it. But it's a pretty simple idea. It's just a displacement law. It's pretty simple. And out of this, what you're getting is the size of this thing in a flow field. So it's actually like the force and then the velocity to pull it and the friction factor. And the friction factor is by Stokes' law, 6 pi times the viscosity of the solvent times the hydrodynamic radius. So this is the hydrodynamic radius that you get out of this. In other words, this is going to be the mass of the chain. The hydrodynamic radius cubed divided by the mass of the chain is this intrinsic viscosity. So directly measuring that RH thing with this kind of measurement. This isn't the only measurement you can do. This is useful. This is useful because in polymers, because you have Purcell's law, so you have like the flux, which is mass per time, is proportional to, I have this in the slides, some geometric constants divided by the viscosity. So the higher the viscosity, the lower the flux. Purcell's law, parabolic flow tank, pipe flow. So that means that time and viscosity are proportional. Like if you flow through a capillary, we have well-developed Purcell flow, a certain volume, right? Measure the time that it takes that volume. So mass is fixed. You just get the time and the viscosity that's proportional to the viscosity. So as long as you measure, you have a start and a stop gates, and you have a stopwatch. You just measure the time for it to flow through, then you get something proportional to viscosity. Right, so you get the solvent viscosity. That's proportional to the solvent time. You get the solution viscosity, that's proportional to the solution time. And if you write this equation out, you have your measured viscosity and then the solvent viscosity ratio, right? So that's the same as the time measured over the time for the solvent, and that's going to equal 1 plus this thing. And if you know how much stuff you dumped in, then you can get that number out if you do a couple measurements in concentration. Right, so typically, so this is usually done with an Uber something viscometer. It's got a Norwegian name or something, I think, that's not German. So it's got like a bulb here, it's got a little track with a perfect capillary. So there's a beginning problem and an end problem, capillary flow. You study flow in the middle, so you want that kind of long. And also, viscosity is proportional to exponential energy over KT, right? So it's Arrhenius. So your T is important. So you put the whole thing in an oil bath because you have to really know the temperature because it's an exponential dependence on temperature for the solvent, right? So and then you have a bulb up here and you let it flow through. So usually we'd like do this in the lab, but it's kind of like, I don't know, this bath is in a silicone oil. It's kind of messy. You have to take this out, fill it, clean it, and we stopped doing that because it got to be kind of goofy. But this is like, chemists like this because they can make anything they want, and then they can just get this intrinsic viscosity and convert it to molecular weight. So you can get like whatever you make in terms of like, get the molecular weight of whatever you made, you know, the thing costs like 10 cents to make. Get a glass blower and make that thing, and that's kind of it. You need a thermometer. So anyway, given this behavior, you have like this intrinsic viscosity is going to be proportional to the molecular weight to this power A. And again, A has those values 28.5, whatever, and some K number. So those are called K and A are called the Mark-Cohen coefficients. You can look them up in a handbook. You can get them at the NIST web book, chemistry web book, or you can kind of just Google it, get the Mark-Cohen. This is Herman Mark, who was also at Brooklyn Polytech. It's like Zim and Herman Mark, and they both escaped Nazi Germany to go to Brooklyn. They're both Jewish, so it's like, anyway, that's how they all ended up. Brooklyn became like a place for all the scientists. Actually, everyone went there, like all the talented people from Germany went there. So, but Brooklyn Polytech was already like the top science school in the US at the time. So there's that business. So that's kind of how you do the intrinsic viscosity. Like I said, normally now people don't do this. They have a high pressure. It's like 60 atmosphere pressure going to a gel, and you get fractions out, and you have a Wheatstone bridge. I guess it isn't wheat. It's pronounced Wheatstone. I don't think it's written that way, but Wheatstone bridge, which is like two columns, one solvent, one's for solution. It splits it, and then that will give you directly the intrinsic viscosity from the column. So you get a small amount of material, feed it in, it splits it in the column, you get the fraction, it spits out intrinsic viscosity for each fraction. If you also have if you have this calibrated, you know the molecular weight, and you get K and A from that. So the variety of ways you can use that rheometer attachment to a GPC. You know, basically, if you know the K and A, you can directly get the molecular weight. That's called the viscosity average molecular weight, MV. But again, like if it's a monodispersed fraction, like MV equals MW equals NN equals NE1, because it's just one number. When it gets to be polydispersed, that becomes important. So here, that directly gives you the molecular weight of the cuts coming off the GPC. This is kind of useful. You couple that with a light scattering, it gives you MW, and then you have the index thing. So you have like 3 detectors on what's coming out. That gives you directly absolute molecular weight value, and you cross-check the viscosity. And you get the K and A parameters. And the A tells you the state of the material. Is it a rod? It's a rod. Is it a theta solvent, beta solvent? Or is it like theta separated or something? Or more importantly, like, is it branched? You know, so that's the big question. So you have the mass that comes out that you measured with the light scattering. And then you have the mass that comes out with the viscometer. They don't agree, right? So the viscometer mass, let's see, in that case, the light scattering is an accurate mass. And this mass, the viscosity is going to be lower than what you expected if it follows the Zim equation, right? Then, because it's in training, it's smaller, so it's a smaller thing. So if the intrinsic viscosity mass comes out smaller than the light scattering mass, you know you have branching, and the ratio of those two can kind of give you the amount of branching in the structure, which is no other way to measure it. Because if you try to do NMR to tag these groups here, but there's only going to be like 1 per 100,000 of those groups, so you can't see it with NMR. It's too small unless you have a really big NMR. So this technique. So this whole setup with all these detectors is about 100K. And the NMR to do this is about 10 million. So basically, and it's questionable if you can do it or not. So basically, this is the way to go. Right, and you can use it for other stuff too. So that's kind of, that's part of this thing. Let me see what I got. So that's part of this intrinsic viscosity thing. I'm missing something, but hopefully I did the projection on that right. For the one thing. So that, all right, yeah, so we got that. So that's how you get this hydrodynamic radius size. Basically, you can just do that measurement. So you can also calculate this hydrodynamic radius. So this is a, so if you want to calculate it for the ZEM model, then you just need to know the mass and the scalings. You just need to know the end-to-end distance of the chain. If you want to calculate it for the draining condition, that's dicier, right? Because it isn't going to be like the rates of gyration. It's going to be something to do with the structure. Kirkwood and Reisman figured out what it would be for total draining. It's like you had all the fluid draining out of it, right? So that's this equation. All right, so I want to show you, we just did some stuff with this, so seems to be timely. This guy Kabir, he's now at NIOSH. He was my grad student, but this is silica, fumed silica. So it's got a number of primary particles that make like a dust bunny kind of. And this is also dust bunnies, but of silver. That there's kind of like a standard thing that they use at NIOSH. They're interested because like if you have an N95, those particles in air, they can penetrate in this regime of size, kind of below a micron, above 0.1. So that's like the part where you can't filter it. And then below 0.01 micron, so 100 nanometer, I guess. Let's see, this is 100 nanometer, that's 10 nanometer, so 100 angstrom. So then they act like molecules. So we call it free molecular regime. They diffuse around a lot, so they don't have like a lot of directional motion. So this region of particles is a lot like chemicals, like in other words, toluene or something, vapor. So it's going to go in your skin. Like the filtering isn't going to make any difference. If you have particles below 100 angstrom, they just go through your eyeballs, through your skin. They just travel right wherever they want to go, they go. Right? So there's no controlling those. The big ones you can collect with a cloth filter. And this is a charged cloth filter, so it's like polypropylene non-woven that's been ionized. Right? So the ions, most of these particles in air are charged, so you can drive them off. But then there's this regime where it doesn't work, you know. Anyway, so they measure the air, that's called aerosol science, right? So there's a whole field of aerosol science. There's about like 100 people in the US doing this, maybe 200, I don't know. So, but within their field, it's a pretty tightly knit community. Anyway, they have their own machines to measure this because it's kind of important. This is a bag of that fumed silica. And then these are the machines they use to measure it with. So these are something like GPCs for aerosols. What they are, they're really set up kind of like a mass spec. So you have the dust and air, then you charge it, you put an electric field on it with 2 plates. So then you have charged particles in air, dust bunnies, dust bunnies, whatever. Then you put them into a centrifuge kind of flow where they have a centrifugal force pushing them out. And they also have like the charge selecting them. So you have charge and mass selection in that thing. And from that, you can get the hydrodynamic radius. It's the same thing we're measuring for polymers, but for things in air, right? So, all right, so you can map that out. He said how to do that. And you can also take those particles, put them in scattering and measure like the structure of it. And then from that, you can calculate the hydrodynamic radius so then from the scattering, you can create the particles again, like the average particle. And then you can calculate the hydrodynamic radius using that equation, that same Kirkwood-Reisman equation. And then you compare it with what you measured with that kind of GPC for particles, right? So if they agree, so that dashed line, then they're not entraining because the Kirkwood-Reisman assumes no entrainment. And if it doesn't agree, it means it's entraining the air as it flows around. So it doesn't have the size that you expect it to have. Right, so the silver doesn't have what you expect, and the silica does. Silica is charged on the surface, silver isn't. So maybe the charging has some kind of way that it prevents the air from sticking. All right, so anyway, so that's kind of like the same stuff. I thought I'd show you that. So is that business? So we don't have a good way to calculate. I mean, you can say it's Zim, which is what everyone does for dilute conditions, but it's not exactly right. And the Kirkwood-Reisman allows you to kind of calculate if it's totally not in training, but actually it's somewhere in between, especially if you have something like something in water, where you have charges, like a polyelectrolyte in water. It's definitely entrained. Definitely entrains the fluid, but to some extent, synthetic polymer. So you don't know. Like this, there's a lot of questions about this hydrodynamic radius. So there's information, but there's also like questions about it. Anyway, if you follow the Zim model, so total entrainment, you can get these kind of ratio between RG and RH. RH in that case would be like the end, really the end-to-end distance, right? So in that case, you can calculate values for like linear chain, RG-RH ratio, and then solid monodispersed sphere is 0.77. So if you get something below 1, it's solid. Something above 1, it's fractal for this ratio of RG to RH. So this paper kind of goes through that. That's our viscometer. That's Purcell's law. That's kind of what I wanted to say about that stuff. So anyway, this gets into these kind of complicated so they have like 3 terms that all look like kind of the same thing. So you have, this is just the viscosity, right? So again, like viscosity, that's weird. So viscosity is just going to be the ratio. You put a shear force, you have like a deck of cards, you push the top card. So your force is going parallel to the surface that you're applying it to. Then the cards form a tilt kind of, right? So the amount of tilt is the flow rate. This fluid sticks to the top card, it sticks to the bottom card, which is fixed. So you have a linear dependence of the velocity across this. And the slope of that velocity gradient. So gamma dot is the velocity. It's like the strain rate. So strain per time, but strain is distance per distance. Distance per time is velocity, and velocity per distance is the velocity gradient. So it's like the slope of the velocity. Right. So right, that's the slope of the velocity, and this is the force that you put on the top card, and the viscosity tells you how much that slope is, like how much it tilts, how far the cards go under a steady state condition. So it's not at equilibrium, it's a steady state, right? So you can't use like thermodynamics to talk about this thing, even though, you know, maybe you'll see that we try to talk about it like it's thermodynamics, right? Because I mean, for instance, like this equation is kind of a thermodynamic equation because you're saying interactions, you have like isolated would be just the concentration. And if you have binary interactions, you square it, so you get, and then ternary, that's thermodynamics when you talk about interactions. So this isn't an interaction, this isn't a thermodynamic measurement, it's a kinetic measurement. When you stop pushing, it stops, you know. Thermodynamics doesn't work that way. Temperature is what's pushing it. Right. So there's an area where people treat this intrinsic viscosity like it's thermodynamic, right? But it isn't. In fact, when you talk about the size of the chain, you know, when you're doing stuff like this and the size of the chain, you're kind of assuming that these are thermodynamic equilibrium structures. So it gets to be a little bit like it works, you know, but it isn't really right to do that. So especially when you start talking about, well, there's interaction between there was a draining, non-draining thing is really the thermodynamic interaction of the solvent with the structure, right, with polymer. So that's thermodynamics, but your base thing when you start with this is kinetics. And the two are separable. They aren't things that you can work together with. Right. So the whole field's kind of a little bit awash with problems. You have to keep in mind when you're doing this stuff that like it isn't necessarily true what people say about it because of that. Because you can't get thermodynamics from this viscometer. Like you just can't. Because it's not at equilibrium, it's flowing through a tube and you're measuring a dynamic property. Right? So you have to be careful, not just with this, but in general, like keep in your mind, there's like a wall. And then on the one side is Ukraine, the other side's Russia or something. Like you don't want to cross that wall if you can help it, you know, because bad things will happen. So basically one side is kinetics, one side is thermodynamics. And they try to reach over all the time to describe kinetics with thermodynamics. It's not so much thermodynamics with kinetics, but you have to read things and say like, is this kinetics or is this thermodynamics? And if it's kinetics, and people are arguing about interaction energies and how that impacts the hydrodynamic effects and things, you have to keep in mind that if it flows at a faster rate or the temperature changes or it's more humid, it's going to fall apart because it isn't thermodynamics at all. It's just like kinetic measurement. So anyway, so they have these three terms to make it confusing, more confusing than it already is. So they have like, see, because you have that equation, so you're going to naturally divide the viscosity by the solvent viscosity. That gives a relative viscosity. Also, two of them begin with R and have an E, so they look the same. So I still haven't figured out how to tell the difference between reduced and relative because it's like too confusing. So reduced is basically the intrinsic, right? Except the intrinsic would be when concentration goes to 0. So you divide, so relative is that divided by that. And then if you take the viscosity minus the solvent divided by the solvent, then that gives you the specific viscosity. And then if you divide that by concentration, you get the reduced. And if you take the reduced and go to 0 concentration, it's the intrinsic. Right? So the reduced concentration should be constant in concentration as long as the concentration is low enough. If it's dilute, in other words.
When you say 0, you mean below C star, where there's no intra-group interactions, right?
That's the idea, yeah. Okay. Yeah, that's the idea. So basically, yeah, it has to be low. So, but then, so see, like things get pretty complicated. Like if you look at a polyelectrolyte here. So this is specific, which is kind of like the intrinsic times the concentration. So you expect that to be linear in concentration if you're in that regime you're talking about. Right? So this one shows that too, specific. So 1 means that it's flat, right? So this is a log scale in concentration. So these are really low concentrations, so it's linear. The blue is polyelectrolyte. The red is not charged. So he has 2-vinyl pyridine, and then you can charge it or uncharge it. So it's neutral when it's red, and blue they put in some kind of salt or something. This is salted out, so it's uncharged, and this is like distilled water is charged. So you have screening when you add extra salt, so it becomes a normal polymer. Then you have, this is almost power 1, right? And then it takes off when you get above C star or entanglement molecular weight. Because here, you can't see C star here, you can see the entanglement kind of, because it's a dynamic measurement, it's kinetics, it's not statics. So when you equate C star and C entanglement, like say the chain straightens out, well, it's not C star anymore. It's still C entanglement, but the chain's deformed in the flow field. So this will depend on the shear rate you put on it, whereas C star doesn't. So that's the difference between thermodynamics and one of the differences, right? So that's why it's complicated. And they haven't mentioned here what the shear rate is, because maybe it was done in a viscometer, maybe it was done under super high, like 30 atmospheres pressure and a GPC. So anyway, like I said, you have to kind of draw that wall between the two things. And when people are reaching over, remember they're reaching over. So anyway, it's power 1. He's making a distinction between 1 and 1.3, and then it shoots up when you get entanglement. It goes to like 3. Right? So, and then if it's polyelectrolyte, it's got some of the transitions that happen, because as you add more polyelectrolyte in, the charges get screened, because when you have the charge on the chain, it's got a counter ion with it. So it's like adding salt. So the concentration not only adds this effect, the 1 to 3, it also adds the effect that you're screening the charges out, and then it becomes a rod. Or it's a rod when it's charged, and it becomes uncharged as you add more concentration, which adds salt with it. Like the polymer carries salt with it. So if you get screening when you add more polymer. So that there's two effects going on. The structure is actually changing, and you're getting this kind of entanglement thing. So this can get to be pretty complicated. Like this guy Colby at Penn State has spent a lot of time thinking about this. So this is again specific. So it's intrinsic times concentration. So it's got proportional to C. So this divided by C would be intrinsic. So proportional means he's got the intrinsic. And then it actually decreases, right? I mean, the intrinsic would decrease in this regime, right? So this is he's distinguished between the overlap concentration and the entanglement concentration. And then he's got a point where you've added so much that you screen out the charges. And then it's not a polyelectrolyte anymore. And then you get this other regime, C double star, and he calls that the electrostatic blob overlap concentration. So you can see, like, these are things you probably don't want to know about unless you have to, because it's going to get really involved. And again, it's a kinetic measurement. So all this should depend on shear rate too, right? And maybe temperature and some other stuff. So anyway, so that's kind of where this is going. So we got these 3 terms, and people toss them around loosely. So it's confusing. I'm not sure how you keep track of them. I still have to look back and see what are they talking about. Because you'll just see, like, he just plots specific viscosity versus the other thing. Like, you have to figure out, like, what is the specific viscosity? And he shows it has a power law dependence of 1 at low concentration. You say, like, that should be flat, but it isn't, because he's taken the concentration part. So there would be, in the reduced would be the intrinsic. Anyway, so that's the least of the problems. So then engineers make a power series of it. That's the first thing you do. If you got something, you have no idea what's going on, power series should work. If you get enough terms, there you go. Bingo, we're out of here. So I was going to show you guys this talk. Like last week was a physical society meeting. This week's a chemical. So there's a big thing now is machine learning and experiments now, to put machine learning into experiments. So someone's taking the coil size measurements from scattering, and then trying to get these power laws, like the 1/2, the 5/3, whatever, 1 for rods. And then like just take a system where you change the solvation condition from good to poor, and then just feed that into machine learning without any theory to do it, and then predict like how you can predict those powers, you know, and then extrapolate the powers to other conditions. So anyway, I thought it would be a good thing to look at, because we've been talking about that coil scaling thing, but I think it's a 40-minute talk, and I could only play it in here. I could still play it. I might do it on Wednesday, but it might be worth looking at. But it's kind of off track a little bit, except that everyone's doing this machine learning thing now. So anyway, so you can take this power series. That's one way to go. Then if you want, like in the paper, so for the homework, you can say this 1 plus that is like exponential. So what the Martin equation does is say, I have the 1 plus. So I'm gonna divide by the solvent viscosity, get the relative. Is that right? Yeah, okay, the relative, see, I can't figure this out. Like, anyway, so then you get 1 plus concentration, the first term, so call that 1 plus concentration times that. So you just take that part out of the next terms, and you have a 1 plus something plus something plus something power series. Right, so you take the first term, you accept that. And then you take the second term, you accept that, but then you say it's going to just be a modifier to an exponential for the rest of them. Like this would be that thing times 1. This would be that thing times concentration times intrinsic. This would be that thing times concentration squared times intrinsic squared, presumably by 1 factorial, 2 factorial, 3 factorial, like to get the real power series thing. So anyway, then I mean, to get the real conversion to exponential, then you just say like that's what it is. So I just have exponential this thing for the rest of all the terms to infinity. Right. So that's one thing you can do. So that kind of works. You know, that's called the Martin equation. It deals with when you get above, I mean, binary interactions, whatever. It deals with all the interactions and higher. I mean, there's approximation because these constants aren't the same. Like ternary isn't the same as binary. So there isn't just one K, there's a different K for every kind of interaction. That's the assumption of it. And then, so that's the Martin equation. Then there's a Huggins equation is just kind of the Martin equation, but just the first term, like the square term of it. And then the Kramer equation is similar to the Martin equation. It's going to be like exponential of this whole group. So you can, hopefully you can see how that, forget about the log, take the exponential of C times that and you can get it out of this equation. So this Kramer equation is another one. People, I mean, you could write a lot of equations if you wanted to do this. Like basically you could do a lot of equations. Each, you keep adding terms. The idea is like to just have one extra term to describe this kind of deviation, like this little divot thing that happens. All right, so anyway, so you're going to get some kind of, as the concentration increases, because the things entangle, you're going to get an increase in viscosity, usually, unless it's a polyelectrolyte, and then you could get, because of the charge buildup, you get screening of the charges, and you get a decrease. Because the thing goes from a rod or an expanded coil to something collapsed, so this intrinsic would drop down. Right, so depending on like what's going on, a lot of things can happen, and there's basically an equation that can describe any situation. These are against molecular weight. So you expect the intrinsic to go up with molecular weight, be like to the square root of molecular weight if it was Gaussian. So the slope should go up. Let's see, specific divided by concentration is, specific divided by concentration is reduced. Oh yeah, I even wrote it right there, it's reduced. Right, so this is reduced. So this should be the intrinsic. This should be flat. So this is for, this is a polyelectrolyte, that's why. This should be flat. This number should be flat at low concentration, but it goes up because it's a polyelectrolyte. This should be linear. Reduced should be the intrinsic, so it should just be a flat number. This is from, there's a book, this Cluck and Klassen, that's on the webpage if you want to go into this more. The main twist is this idea of the polyelectrolyte stuff. So this is the Einstein. So I already went through the dimensional thing. So if df is 3, that's 1 minus 1, that's 0. So you just have a number there. And 2.5 is a number to remember. And then the Zim model. So that's basically based on the Zim model. And then, so yeah, people, this is just looking at this charge effect in polyelectrolytes. Like there's weird things that can happen with this. So people, like there's many PhDs looking at intrinsic viscosity. Police activity. More information soon. Luckily, we're stuck here. Temperature dependence is Arrhenius. I went through this already, right? I went through like how WLF fits in with this stuff already, I think, didn't I? Like you have Arrhenius, and you just say, I mean, the idea is that that was enthalpy. So you can have that Arrhenius behavior. There's it would be enthalpy minus TS. It would be a temperature dependent part if it was energy. So if you add the temperature dependent part, you get another term besides that. This is a two-term equation if we factor in that. This thing becomes 3 when you add in the entropy. If you say the temperature isn't based on absolute zero, you say it's based when the motion stops for viscosity. Like when the viscosity shoots through the roof, that happens at the glass transition, or generally at the Vogel temperature. So see, that adds in another term. So you end up with 3 constants. You have the prefactor, H and S, that's 3, and then TV is 4. That's 4 constants. Somehow I got 3 out of that. One, 2, 3, 4. Anyway, I didn't notice that, but because AT is a ratio of the two, so the A drops out. AT is a ratio of viscosity at some temperature to the other viscosity, so there is no A. So there's only 3 terms. So if you the WLF equation is this idea of just talking about this in terms of energy and adding a Vogel temperature is this thing. So you can work out what these 3 parameters in the WLF are if you wanted to talk about in terms of enthalpy, entropy, and Vogel temperature, ground temperature. And they are given down here like the Vogel temperature C2 minus TR, entropies 2.3, because this is base 10, this is exponential. So 2.3 times C1, HA is 2.3 times C1 times TR. So you can directly convert the WLF parameters to entropy and enthalpy of activation for going over a barrier for flow. Right, the Arrhenius thing's based on this idea of flow is just you have your things, you have the thing that wants to go over there, it has to go through this activated energy state. So the energy is here, the energy is there, and there's a peak. So there's an energy of activation for flow to happen. Right, so that's kind of the basis of the Arrhenius equation, and that's the basis of everything that you talk about with kinetics when you have an energy. And so hopefully that makes sense, the temperature dependence part. So it's strongly temperature dependent. This guy, Simha, at Case, spent his whole career, Polymer science at Case, spent his whole career from like 1920 to 2000 something, doing just kind of like objects using this intrinsic viscosity and figuring out what this term is for like proteins and stuff, like the different shaped objects. Sounds kind of dry, but he was pretty successful. That's what he did. So there's a book on him, and in this Clausen book, they go through a whole thing about his equations for figuring out for different shape objects, how that would work. Significance, I mean, for analytic for proteins, like native state proteins, it's kind of important. Ribonucleic acid, tobacco mosaic virus shape was discovered by Simha, like the idea that it's a rod, I guess, using this approach. And then again, like branching, like the behavior with branching, you can get that information from this intrinsic viscosity. Like so they'll take the intrinsic versus the linear intrinsic, take the ratio and come up with a number, this number G, and then from G you can tell like how branched something is. That gets to be a little involved. So basically people are interested in branching, especially polyolefins like polyethylene, and this is one way to do it. Is this intrinsic viscosity ratio between a branched and a linear. and it's related to the functionality. Anyway, so we're out of time. So that's probably enough. I'll probably find a paper on some of this branching thing or something. And so next time I'll talk about hydrodynamic radius from dynamic light scattering.